my name is Andrea Ciardiello. I am with the Italian National Institute for Nuclear Physics, and I will talk you about my work about explainable deep learning inference to decode decision-making process from multidimensional pattern of neural activity. That is a part of the MUCA project that stands for multidisciplinary use case. Oh, thank you. For convergent new approaches to artificial intelligence explainability. For this audience, I should clarify that in this case, I'm talking about machine learning. So one of the first aim of this project is to adapt and specialize explainability artificial intelligence to different use cases. As you know, machine learning algorithms are seen as black boxes, and there is now a growing interest on algorithms that can help understand how they work. One of the use cases selected is neuroscience. So, unfortunately, we are a little bit far from the topic of today. So I will start to have a little bit of details on this one. In the experimental context of these studies is countermanding experiment. That is, are two monkeys that are trained to move their hands from a central location to a target when a certain stimulus is given. In a subset of these trials, another stimulus, a stop signal, is given after a delay time that is called a stop signal delay, at which the monkey should inhibit their movement. We call the time that pass from the go signal to the movement onset the reaction time. A common way to describe phenomenologically from a behavioral perspective this kind of tasks are the later model, in which after a stimulus, a decision signal starts growing linearly to a threshold. When the threshold is reached, then a response is made. The ramping rate, the rate of the decision signal growing is inversely proportional to the reaction time. So what we are trying to do is to map data recorded from a 96 Utah array, the multi-unit activity recorded from the premotor cortex to the theoretical model that we can derive from the later model. We will use a causal artificial neural network, and our goal is to do an early estimation of the reaction time through a fit of the early part of the decoded ramp. So in particular, there is a little details to give about the neural network architecture used. That is that we need a causal architecture. A causal architecture means that the ramp is inferred only from past data, and all neural data is provided as an input. We trained two different approaches. One is a sequence-to-sequence causal artificial neural network inspired by the WaveNet, and the other is a simple multi-layer perception that have the task of regress the position on the ramp from a small 20 millisecond snapshot of neural activity. So, details about the training. We have two subjects, 6 sessions, 8 sections for subject 1 and subject 2. The section as months are recorded in a span of a few months. What we want to do is test the generalization ability of this method. So each session is trained only on other past session. Early prediction is performed only through extrapolation of the ramp time before the average stop signal delay for the session. The network is trained only in the task where there is no stop signal and is trained on both subjects together. What I want to that you can see that it is possible to do this early estimation with good accuracy. Here there is the early estimation from the fit, and this is the localization of the movement onset. So as you can see, it's possible to generalize intersessions, so through time. Also, the performance are maintained when we test on wrong stop, so stop at which the movement was not inhibited, and also on correct stop. In particular, on correct stop, we can see how, as described by the extension of the model to the presence of the stop process. So as a process that starts later and also run through the threshold, movement is correctly inhibited when this stops process reach the threshold before the go signal. So to be correctly cancelled, the reaction time for a correct stop is usually larger, have to be larger than one for the wrong stops. This stop signal reaction time can be estimated as a behavioral level from the session. We can measure it through our method, and the two results are in agreed accordance. As you can see, like a snapshot from two sessions, the correct stop reaction time that are not existed but are only estimated from an early estimation of reaction time, those are correctly inhibited, are larger than the measured wrong stop. So let's talk about how explainability algorithm can help understanding how this kind of generalization is possible, generalization through time. So I will talk about this influence function. Influence function are a type of instance-based interpretation methods. Instance-based interpretation are about giving a score that measure relation between a point in the training sample and point in the test sample. So for example, you can say this image is labeled by the network as a cat because this other image that was in the training are also cat, and the networks see them as similar. In particular, influence function is computed by removing an example of the training set and checking how this remotion influence the performance of some test example. Unfortunately, influence function cannot be computed directly in many applications because they require to train multiple times the network. So in this case, we're using the track-in method that is, let's say, an effective way to estimate influence. So what you can see that if you order trials by reaction time for two sections, one section in the test session and one test in the pass session in the train session, you can see that take the track-in score as a similarity index. You can see that correctly the network managed to put together slow reaction time with slow reaction time and long reaction time, fast reaction, and with long reaction time. In the same way, it can put a great distance, so a negative score between long and short reaction time. This is expected. What was not expected that also if the network is trained on two subjects together, then a different example from different subjects, so subject 1 versus subject 2, also exhibit the same pattern. This is hinting at shared representation inside the neural network, and also that the two subjects are seen as a different example of the same project, the same process. So what also can we learn by Xi methods that are usually called a saliency map. Saliency map are a way to understand which part of the data are used to make the prediction. We adapt for this kind of data and this kind of task two methods that are widely used. One is the integrated gradients. That is a backward method that involves many passes of backward call to the model. And what we can ask to this method is, for example, which electrodes are mainly used to make the prediction of the ramp. And as you can see, the method return a very sparse matrix. This is the saliency, so the score of importance for each test prediction reported on the electrical of the electrodes grid. Another common application is to do a local linear approximation of the model and then invert it. By the inversion of the local model, we can do an output perturbation. So we can modify the parameters of the theoretical model and see how the output is then modified. So for example, we can see that increasing or decreasing a little bit the steepness of the ramp, the vast majority of the information is near or maybe even before the go signal. So the reaction time can be estimated by a very short time frame near the go signal. So to conclude, we saw that it's possible to build a map between error recording and a theoretical behavior model. This approach has interesting performance in the prediction of the reaction time and also can generalize very well to different sessions acquired in different times, even months apart. In particular, inferring the ramp instead of directly the reaction time can give us new opportunity to better understand the underlying process, and also we can apply explainability method, the perturbation one, through, let's say, direct perturbation of theoretical parameters. So doing the perturbation not in a random way, but in a principled way. Also, we have seen that we can found temporal and spatial patterns in the data, and they can be used to better understand which information are used to generalize. The natural evolution of my work is a real-time application, because this model, once they are trained, have a very, very fast latency, a very, very short latency and fast inference time, so they can easily ported online in real time. And we hope to better develop explainability tool to also act as discovery tools for this kind of new data. So thank you for your attention, and I'm available for any question.